Why is it that when you go up in an airplane or go up in the mountains, it feels like your ears are actually popping? That has to do with gas pressure, and that's what today's topic is all about. So let's define what we're talking about first, and this is going to connect with what we've talked about yesterday and today a little bit, and the day before when we talked about kinetic theory and how um, all molecules or all substances are made of molecules. Molecules are always moving, especially gases, and that's what we're going to focus on today. So gas pressure is where we start off with. Now, gas pressure itself is the force that's exerted. Now, in physics, a force is just a push or a pull. If you run into something, you exert a force on it. Something runs into you, it exerts a force on you, push or a pull. So gas pressure is going to be the force exerted by a gas particle per surface area of an object. What that means is here, we've got in this box here, we have gas molecules. And as we know now, gas molecules are small particles that are moving very, very rapidly, and they bounce off of each other and off of the walls of the container that you put them in, and they fill up the container. And the collisions are perfectly elastic. They don't lose any energy when they bounce off of each other. So as you can see, like this, we'll take one of these, like this little guy right here, as it bounces off the surface of this container, it's going to create a pressure. It's going to push a little bit. And there's another one bouncing off, more pressure, another one, more pressure, and more pressure, and more pressure. So the more gas particles that are in there, the higher the pressure, and the greater the temperature, the higher the pressure as well. But that's what gas pressure is. It's just anytime there is gas molecules present, they are going to create a pressure. Now, we scientists measure gas particles a couple different ways, or pressure a couple different ways. And one of the ways, or both of the ways actually, is using a barometer. So we say gas pressure is measured with a barometer in here. Here's one type of barometer. And so as the pressure increases, there we have one of these little arms on it, and that arm can move as pressure increases. And sometimes if you watch the weather, on the news, they'll talk about a high pressure system coming in, which typically tells us it's going to be really dry. So here in California, sorry about that, here in California in the summertime, we often have high pressure systems over the top of us. It's very dry, hot. And sometimes we have low pressure systems, and that's going to be an indication of a stormy weather, some rain and some wind and things like that. So that's one way we can measure gas pressure, is with our object called a barometer. We also have a mercury barometer. This is a mercury barometer. And this is how a mercury barometer works. We take some liquid mercury, and it's placed in a tub. And then we have this glass container like this that's sealed at one end, and it's going to be open at the other end. And we're going to completely fill that guy up with mercury, and then we're going to invert it into the dish of liquid. Now what's going to happen is we're going to get this mercury level is going to drop just like this. And as the mercury level drops, it's going to leave a space here, and the space we're going to call a vacuum. Now, the definition of a vacuum, which is a really important idea, definition of vacuum, and you should definitely jot this down, is going to be an empty space with no gas particles. Now, if we don't have any gas particles in that empty space, we have no pressure. There's no gas particles to bounce off of the interior walls of that. So that's what a vacuum is, an empty space with no particles. So what happens is this is used to measure gas pressure. So as the atmospheric pressure, now atmospheric pressure is going to be our gas molecules that are all around us, the oxygen that we're breathing, the carbon dioxide, the nitrogen gas, all those gases that make up our atmosphere. They will exert a pressure. They exert a pressure on us, they exert a pressure on everything around us, and they'll also exert a pressure on this column of mercury. They will be able to push down. Now that pushing down on the column of mercury pushes the mercury up, and so this mercury level can rise and fall depending on the atmospheric pressure. So this is a mercury barometer that measures gas pressure. Okay. Now, the last thing that we're going to talk about is we have some units of pressure that we commonly use in chemistry. Now, there's many other units of pressure. For example, if you were to go to the gas station and you were to pump up the tires on a car or truck, you would probably measure gas pressure in PSI, which is pounds per square inch. But in chemistry, we don't typically use PSI as a unit of pressure. In chemistry, we are going to use a couple other units of pressure commonly. And so we had talked about before STP. We talked about it when we did mole calculations of stoichiometry. We said if you were at STP, you were actually allowed to use 22.4 liters equals 1 mole as a conversion factor. That was called standard temperature and pressure. Because gases are so affected by temperature and pressure, we have to have a standard measurement. Now, that standard temperature we talked about before is 0 degrees Celsius, and the standard pressure are going to be given below. Our standard pressures are 1 atmosphere. Another one of them is 760 millimeters, a unit of measurement of mercury, that's using the mercury barometer, and also a standard unit is 101.3 kilopascals, 101.3 kPa. These are all given to you on the back of your periodic table, so you don't really need to memorize them, you just know how to use them. And we're going to use them in pressure conversions next. So let's take a look at some pressure conversions. And these are really easy to do, and they work real similar to a mole concept. So let's take a look at them. So the first pressure conversion is going to be convert 2.5 atmospheres to millimeters of mercury. So what I'm going to do is I'm going to identify my known quantity, just like I always do, like in mole calculations. So my known quantity here is 2.5 atmosphere. And I'm going to make a little grid just like this, just like our picket fence that we made. Let me scoot this down a little bit. Our picket fence that we made in mole calculations. And so I'm going to take my known, and I'm going to put it right here, 2.5 atm. And then I'm going to identify my unknown. In this case, my unknown is millimeters of mercury. And I'm going to place that right here, millimeters of mercury. And so what I'm going to do is now use my conversions. I'm going to use the conversion that involves atm and millimeters of mercury. So if we look at this equality that we have up here, we have 1 atm is equal to 760 millimeters of mercury. So we're converting from atm to millimeters of mercury. So I'm going to go ahead and place the number 760 in front here. That's this conversion. And on the other side, we have 1 atmosphere. And we're going to place 1 atmosphere on the bottom, just like that, so that our atmospheres cancel. And we're going to multiply across and get an answer with millimeters of mercury. So let's do that real quickly here. And I get an answer of 1900 millimeters of mercury, or we could also put that in scientific notation, call it 1.9 times 10 to the third millimeters of mercury. And so that would be our pressure conversion, and pressure conversions will be useful coming soon when we start dealing with gas laws. Let's take a look at one more. And it says convert 150 kPa, there's our known, and we're going to go to millimeters of mercury. So let's set this guy up just like we do on his. And so we have 150 kilopascals, and we're going to convert it to millimeters of mercury. So we're going to use the conversion factor up here again, and we're going to use just the kPa in millimeters of mercury. So if you see that there, we have 760 millimeters of mercury is equal to 101.3 kPa. 760 millimeters of mercury is equal to 101.3 kPa. And so in front of millimeters of mercury, we're going to put 760. And on the bottom down there, we're going to put 101.3 kPa. We know we used the kPa and not the atm because our known value is a kPa. And so in this problem, what we're going to do is we have to multiply and then divide. So 150 multiplied by 760 divided by 101.3 kilopascals. And the answer that I get 1125.370 millimeters of mercury, because kilopascals unit and kilopascals are going to cancel. We do have only 2 sig figs here, so let's go ahead and put this in scientific notation and call it 1.1 times 10 to the third millimeters of mercury as our answer. Okay. Now, so this tells us essentially what we talked about today. Just a quick review is we did talk about how gas, by running into things, creates pressure. We talked about how we can measure pressure using a barometer, whether it be a regular barometer or even a mercury barometer, a regular barometer called aneroid barometers. And then we can also talk about how we can convert from one unit of pressure to another unit of pressure. And the 3 common ones that we use in chemistry are atmosphere, millimeters of mercury, and kilopascals. And so there will be some practice problems that go along with this.